Buenas tardes a todos. Muchas gracias por haber venido. Me llamo Antonio Pic, soy el coordinador del proyecto CEPAN, el Centro Nacional de Física de Partículas, y hoy tengo el enorme placer de poder introducirles a nuestro conferenciante de hoy, el profesor Rolf Heuer, director general del CERN. Él nos va a hablar sobre el Higgs, que ha sido un tema científico de gran actualidad durante los 2 últimos años, y espero que después de esta conferencia nos quede a todos muy claro por qué es algo tan importante. Antes de nada, quisiera agradecer a la Fundación BBVA por la oportunidad de haber creado este ciclo en el que poder llevar toda esta serie de conferencias e ideas a todos ustedes, y en particular por la oportunidad de poder traer aquí al profesor Rolf Heuer, que no es tan fácil hacerle venir. Quisiera empezar, vamos a hablar del Higgs. ¿Por qué el Higgs es tan importante? Ha de ser muy importante porque ha salido en todos los periódicos, porque ha salido en los periódicos de economía, no necesariamente en los medios científicos. Es importante, y hay que hacerse a la idea, para los físicos básicos es algo muy importante. Nos cierra de alguna forma un paradigma, el llamado modelo estándar, que ahora veremos lo que es. Para hacernos una idea, para los físicos es algo equiparable a lo que fue para los químicos en su momento el descubrimiento de la estructura atómica, o para lo que fue para los biólogos en su momento el descubrimiento del DNA. Es algo que realmente abre un camino nuevo, ¿vale? De hecho, nos cierra un paradigma y nos abre muchas preguntas. Es algo que no se descubre así de casualidad en un momento determinado. Es algo que se le está buscando durante muchos años, ¿vale? ¿Por qué? Es la pieza que faltaba para cerrar nuestro modelo estándar de las interacciones fundamentales. Y ahora la pregunta es, ¿qué es eso del modelo estándar? Eso sería el modelo estándar hace 150 años, ¿vale? Todo el mundo está familiarizado con esta tabla de los elementos. En su momento fue algo muy importante en ciencia, ¿vale? Una vez alguien fue capaz de ordenar todos los elementos químicos en esta tabla, los elementos químicos eran las estructuras más básicas de la materia, del mundo conocido. Pero además en esa ordenación pues hay un numerito, 1, 2, 3, 4, ¿vale? Que quería decir algo, no se sabía muy bien lo que era, ¿vale? Pero tenía que tener un significado. Luego habían familias, elementos que tenían las mismas propiedades. Y para un químico tener la tabla en la pared significaba pues saber qué tenía que meter en la probeta, con qué lo tenía que mezclar para obtener el resultado esperado. Por supuesto, la tabla contiene toda esa información, pero los científicos no eran capaces de reconocer la información que tenía la tabla. Fueron capaces de reconocer esa información cuando entendimos que existe la estructura atómica. ¿Vale? Cuando entendimos que todos esos elementos, ese numerito 1, 2, 3, 4, está contando el número de electrones que están dando vueltas alrededor del núcleo. Y por lo tanto, los 100 y pico elementos químicos quedan reducidos a una partícula, el electrón, y una interacción, la interacción electromagnética. Eso es realmente una gran simplificación del mundo conocido. ¿Vale? Esa simplificación introdujo el modelo atómico, revolucionó la química, pero también revolucionó la física, nos introdujo la mecánica cuántica, una de las 2 grandes revoluciones conceptuales del siglo XX. Pero luego hemos ido aprendiendo muchas cosas. Los electrones giran alrededor de algo que tiene carga positiva. Ese algo es un conjunto de protones y neutrones que, para que se puedan mantener juntos y el electromagnetismo no los repela, hace falta que haya una interacción mucho más fuerte que los mantenga unidos. Esa es la llamada interacción fuerte o interacción nuclear. Hemos aprendido que protones y neutrones no son partículas elementales, están compuestos de quarks. Y esa es la interacción fuerte la que está manteniendo esos quarks dentro de los protones, y que igual que existe el protón y el neutrón, pues existen cientos de partículas formadas por quarks, entes compuestos. ¿Vale? Por tanto, ya tenemos dos tipos de partículas, el electrón y los quarks, dos interacciones, la interacción electromagnética y la interacción fuerte o nuclear. Hay una tercera interacción mucho más sutil y mucho más tenue. Se llama interacción débil, porque es muy débil. Y es una interacción que también los componentes del núcleo atómico y los electrones sienten, y es la interacción responsable de las desintegraciones radiactivas, de la radiactividad natural, del funcionamiento del Sol. Es extraordinariamente importante. ¿Qué es el modelo estándar? Pues el modelo estándar es una descripción teórica de estos componentes fundamentales de la materia y de estas interacciones básicas. Es algo que está basado en las dos grandes revoluciones conceptuales del siglo XX, la mecánica cuántica, que describe los objetos muy, muy pequeñitos, y la relatividad especial, que describe aquellos objetos que van a velocidades muy grandes, la velocidad de la luz. En este marco conceptual es donde se ha formulado el modelo estándar, que es capaz de describir todos los fenómenos electromagnéticos, eso quiere decir electricidad, magnetismo y luz, de una forma unificada, con una teoría unificada, con la interacción débil, y las describe mediante el intercambio de fotones, los rayitos de luz que vemos en los centros comerciales al entrar en la escalera, y las partículas pesadas Z y W, que es de las que va a tener que hablar nuestro conferenciante de hoy. Otra parte del modelo es la llamada cromodinámica cuántica, que describe realmente la interacción nuclear, la interacción fuerte. ¿Por qué es tan elegante el modelo estándar? Porque está absolutamente todo basado en principios de simetría. A partir de una simetría pura en el espacio-tiempo se deducen todas las leyes que gobiernan las interacciones. ¿Vale? Es de una forma muy económica, matemáticamente extraordinariamente elegante, muy predictiva, y todo aquello que el modelo estándar ha sido capaz de predecir lo hemos podido medir con grandes precisiones y funciona. Por tanto, es una teoría realmente muy buena, de la cual los científicos estamos muy orgullosos. El modelo estándar nos ha traído también una tabla periódica. Esta es la tabla periódica del siglo XXI. Igual que la tabla periódica de hace 150 años, contiene una gran cantidad de información. Parte de esa información la entendemos, nos la explica el modelo estándar, y parte de esa información no la acabamos de entender. Son preguntas abiertas que siguen ahí, pero que nos está dando algún mensaje que tenemos que seguir buscando. ¿Qué nos dice esta tabla? Bueno, tenemos aquí las tres interacciones: la interacción electromagnética, que viene mediada por fotones; la interacción fuerte, que viene mediada por gluones; la interacción débil, que viene mediada por estos objetos pesados. La tabla nos dice que todo lo que está a nuestro alrededor, toda la materia ordinaria, la podemos explicar simplemente con cuatro partículas: dos quarks, el electrón y un neutrino. Y eso, con nuestro modelo estándar de las interacciones, lo explica absolutamente todo. Sin embargo, en el laboratorio, haciendo experimentos, o cuando el Sol nos manda rayos cósmicos desde arriba de la atmósfera, pues hemos aprendido que existen otras partículas de materia. Hemos aprendido que todo está replicado 3 veces. ¿Por qué todo se repite 3 veces? No tenemos ni idea. Y el modelo estándar no nos lo explica. Solo sabemos que tiene mucho que ver con el hecho de que nosotros estemos aquí. Tiene que ver con la simetría entre materia y antimateria en el universo. El hecho de que el universo está formado por materia y la antimateria ha desaparecido. ¿Vale? Con 3 familias, el modelo estándar puede tratar de entender eso. Con uno sería imposible. Luego he puesto aquí el Higgs, el ente nacido hace poco, que llevamos muchos años buscando. ¿Por qué es tan importante? Bueno, es tan importante porque las mismas simetrías que nos han dado lugar al modelo estándar, que nos han explicado lo que es, nos predicen que todos estos objetos tienen que tener masa cero, lo cual es un desastre. No entenderíamos nada. Nos quedaríamos muy contentos para el fotón y los gluones. Sabemos por qué viajan a la velocidad de la luz, porque tienen masa cero, pero es totalmente imposible entender por qué estos objetos son pesados, por qué este otro objeto es pesado. La masa es justo la diferencia entre los objetos. El campo de Higgs y el bosón de Higgs fueron introducidos hace 50 años para resolver este problema. Y durante este tiempo hemos intentado entenderlos. La forma de buscarlos ha sido un gran proyecto internacional, una gran colaboración. Ahí el CERN es donde ha tenido el gran logro de poner todos los países del planeta juntos en un gran proyecto internacional. Y el profesor Rolf-Dieter Heuer nos va a hablar de cómo eso ha sido posible. Y, por supuesto, el resultado ha sido el que todos conocemos. Ha habido un gran descubrimiento, ha sido un gran éxito del modelo estándar que todos estamos celebrando. El mérito es un mérito compartido de mucha gente. Y como todos sabéis, pues se ha visto inmediatamente recompensado tanto con el premio Nobel como con el premio Príncipe de Asturias. Aquí tenemos la imagen con el profesor Rolf-Dieter Heuer recogiendo el premio Príncipe de Asturias. Quiero solo mencionar que por una vez en un gran descubrimiento científico, España ha tenido una participación muy relevante. Los científicos de nuestro país han estado contribuyendo desde muchos laboratorios a construir partes muy importantes de los detectores. Estamos hablando de alta tecnología, tanto en los institutos de física, fundamental, como en empresas españolas, se han estado diseñando y fabricando toda esta serie de objetos. Hace 7 años la comunidad fue consciente de que era necesario dar un impulso, de que teníamos un gran reto por delante, de que teníamos grandes compromisos internacionales para este proyecto que era necesario atender, era necesario garantizar que todo aquello que España estaba construyendo fuera a funcionar, y se lanzó un gran proyecto, el proyecto CEPAN, para asegurar que todo funcionara. Ha sido un éxito, la comunidad española ha estado trabajando de forma coordinada en el CERN y podemos asegurar que todos aquellos aparatos y detectores bajo responsabilidad española han funcionado perfectamente. El CEPAN, desgraciadamente, se acaba el año que viene y estoy seguro que nuestras autoridades estarán ya pensando en qué hacer para poder seguir, porque hace falta proseguir, porque justo el año que viene el LHC vuelve a entrar en funcionamiento, vuelve a afrontar un reto mucho mayor, más energía, más intensidad. Van a haber grandes descubrimientos y nuestra comunidad científica sigue estando comprometida, sigue teniendo grandes responsabilidades y las cosas tienen que funcionar. Bueno, de todo esto nos va a hablar el profesor Rolf-Dieter Heuer. No voy a repetir todo su currículum. No solamente es el director general del CERN, es un gran científico con una gran trayectoria en muchos experimentos, con grandes responsabilidades científicas, y ha sido el director general bajo el cual se ha descubierto el Higgs, por lo tanto tiene una gran responsabilidad en este descubrimiento. Sin más, it's an honor to have you here, so please, we are waiting for you.
Thank you very much, Antonio. Makes my job now easier because you will understand the standard model very easily also for my talk now. But before I go into the Higgs boson and the LHC, I want to tell you that this is, in Spain, the last event celebrating 60 years of CERN. 60 years of science for peace and 60 years of technologies and fantastic evolution in science. And the title I have chosen is What the Discovery of the Higgs boson tells us about physics, about mankind and the universe. But not all of you might know CERN already, so first I want to give you the mission of CERN. And the mission of CERN is fourfold. First of all, research. That's the raison d'etre why CERN was founded 60 years ago. But everybody knows you cannot do research at the forefront of science without innovations, innovating technologies. I mean, this is very, very important. You can use it to educate, to train people. We need people trained in science, in engineering. They are the future. For a sustainable future, we need trained people. And you have to learn that you cannot do it alone. You need everybody. Yeah? You need the small countries over here. Okay? So we need you. Okay, that's very far here. You accept that we also need you, okay? You cannot do it alone. So CERN is a fantastic place to unite people. In research, we want to push the frontiers of knowledge. We want to push them back. We want to understand how the universe developed. Why can we exist at all? That should interest everybody. Yeah? And in order to do that, we have to develop new technologies. In our case, for accelerators, for detectors. Yeah? So I don't see so many young people. Who is below 30? Oh, at least some of you, okay? Good. You have never seen a world without the World Wide Web. Yeah? 25 years ago, CERN invented the World Wide Web. And it has changed the world. It has changed the world of communication. It has changed the world of economy. So that came out of our research because we needed this way of communication. Okay? But there's also a lot in medical applications, etc. But I don't go into that. Now, pushing back the frontiers of knowledge, innovation and technologies, you must agree that this is a fantastic training ground for scientists and engineers of today and of tomorrow. Yeah? And everybody, each country, independent if it's small or if it's even a large country on this side, okay, needs engineers. Yeah? That's the future. And as I said, one of the main facets of CERN which inspires me most is uniting people, really bridging different cultures, different nations, because we speak one language, and that's science. Science is a universal language. So CERN was founded in 1954, and you have to imagine, it started in 1949. Europe was in ruins. You needed a handful of visionary diplomats, a handful of visionary scientists to get together in scientific language to resonate. And the resonance 5 years later, 1954, was CERN. And since that time, we are, I think, a role model of Europe, what Europe can do if Europe combines its forces. Today, we have 21 member states. And now comes your challenge for the interpreter. Because 2010, we have changed the meaning of the E in CERN from Europe to everywhere. That means each country, independent of its geographical location, can become a member of CERN. And if you look closely, it's difficult to show people. In the second line, Israel is today the first nation outside the normal definition of Europe as a member state of CERN. And you see, when you look who is applying for membership, Pakistan, Turkey, Ukraine, Russia, Cyprus. It's science for peace. You get them around one table. If you leave the conflicts outside the fences, it's okay, and we are trying to do that. Okay, we have roughly 4,000 people on our payroll, but many more people are coming from all over the world in order to do their science. Between 10 and 11,000 scientists are coming. And you see here where the people are coming from. This is not the display of their passports. It is the location of the institutes where our scientific users are coming from. Altogether, we have roughly 100 nationalities registered to work at CERN. And you see they come from all over the world, and we are trying to increase the connections also to countries in Africa and elsewhere in the world where we still have the white spots. One thing which is fantastic is that this is the age distribution of our visiting scientists. And you see, it peaks at 26 years. So we have young scientists coming. And when you come to CERN, when you visit CERN, you will see a bustling restaurant, and all the people are coming together, and they are all very, very young. 26, it's of course the PhD students, not the German PhD students. I'm a German. we are always older. Not much more experienced, but we are older. We have to also reduce the age of the German PhD. See, okay, that's a different story. But it's these young people which drive the field and which drive our future. So I'm very happy. People with very good eyes can see that there's also an entry at 85. Still active. And of course, that's the cheapest manpower. Okay, that's a different story again. Okay, but why do they come? They want to understand the very first moment of our universe after the Big Bang. At the moment of the Big Bang, when it was tremendously hot, a tremendously high energetic spot. And then it expanded over roughly 14 billion years to a size of today 10 to the 28 centimeters. Don't ask me what 10 to the 28 centimeters mean. I cannot imagine. It's a huge number, but it's a very important number in the evolution of the universe and in the understanding of the evolution of the universe. I have here on a ruler the whole history of the universe. On the bottom right, you have the universe today, 10 to the 28 centimeters. On the top left, you have the universe at its beginning, at the Big Bang, 10 to the minus 32 centimeters. Again, impossible, for me at least, to imagine what is 10 to the minus 28, 10 to the minus 24. It's zero. But a tremendous amount has happened on these small scales in the universe. And that is what we want to find out. So how can we find that out? Well, we can go to the large scale. At the large scale, we can use ground-based telescopes, we can use space-based telescopes in order to look into the history of the universe. The more powerful your telescopes, the further back you can look. The higher the resolution, the further back. But there's a problem. And the problem is around 380,000 years after the Big Bang. That's a wall. This is a wall which you are hitting when you are looking with telescopes. Because in the first 380,000 years, the universe was still so hot, so energetic, that matter and force particles were always fighting with each other. One was transforming in the other. No information could get out in the form of light particles. So 380,000 years is the limit to which you can go. It's already pretty close to the early universe compared to 14 billion years. But we want to get closer. So what do? We go to the left top. We go to the small scales. And here comes the big difference. At the large scale, we are looking into the history. At the small scale, we are reproducing the conditions at that moment. That's a big difference. We are reproducing the conditions at that moment in the early universe. How do we do that? Well, we construct the most powerful microscope on Earth. And that's an accelerator, that's the Large Hadron Collider. It's a super microscope with which you can resolve sizes, objects of the order of 10 to the minus 16 centimeters. How do we do that? Well, we use high energy. And for those people who are not scientifically literate yet, I have only 3 equations in my talk. And here are the first 2. So don't get worried. With a higher energy, you have a smaller wavelength. The smaller the wavelengths, the better your resolution. So good resolution means higher energy. That's a law of nature, so we need high energy in order to resolve the inner structure of matter. So the higher the energy, the higher your resolution power. But high energy has another advantage. Higher energy, according to Einstein, you can produce new particles with higher mass. So the higher the energy, the more massive a new particle can be. This is the way, by the way, we found this famous Higgs particle, because we had higher energy. And the big advantage of accelerators is you can always repeat the experiment. Every day, every second, million times, etc. So you get precision measurements, you get high statistics, precision measurements. That's the advantage. How do we accelerate particles? And now I must apologize to Miguel. This is a very easy accelerator, which I show now. We accelerate through electric voltage. Take just a battery of 1 volt. The proton has a positive charge of one electron, equivalent. So the proton going from the plus pole to the minus pole acquires an energy of 1 electron volt. That's our unit. Now 1 electron volt means for the LHC that we are working in TeV range, that is 1 times 10 to the 12 electron volt. Which means if we would use batteries, we would need for the energy of the LHC 14 batteries per star in the Andromeda galaxy. That's a large number. So we do it differently. But this gives you an idea of the energy. Okay, so we have the LHC. And with this, we get closer to the Big Bang than anybody else. We get as close to the Big Bang as 1 billionth of a second, 10 to the minus 12 seconds. Nobody else gets closer. In that way, we are really breaking the wall of this hidden universe behind the 380,000 years. And this is what gives us the information about the early universe, about the forces, about the particles. Now, what have we learned? And you saw this already in Antonio's talk. We know that more than 100 years that the atomos are no longer atomos. They can be divided into the nuclei and the electrons, which means, actually, I'm sorry to say it, you are essentially all empty. No, me too, okay? So it's the forces which makes our mass and our matter, but the matter particles are really concentrated essentially into in the nuclei. Afterwards, we learned that the nuclei consist of the protons and the neutrons, and in turn, the protons and neutrons are consisting out of the quarks. And these quarks are today's atomos. And now let's see what we have learned, what you have already learned from Antonio's talk. This is our so-called standard model of particle physics. He showed you the periodic system of the elements. Is there somebody who studies chemistry or has studied chemistry? Yeah, you can tell it. Oh, there is one at least over there. I'm sorry to say, but I think, yeah, don't you agree that particle physics is much easier than chemistry? This is a much easier periodic system. Okay, so you have learned already today that there are 3 families of 2 quarks, up, down, etc., and 2 leptons each. So 3 families of 2 quarks and 2 leptons each. 12 matter particles. Why 12? Because, as you just have heard, we all are only made out of 3 particles, 3 matter particles. Yes, it's true. We only need 3 matter particles in order to construct us. The up quark, the down quark, and the electron. Why do we have 3 of these families? We don't know. But we know that we need at least 3 in order to explain partly why antimatter has disappeared. Only partly, not fully. Okay, so. But the matter particles alone don't make us. We need the force particles which communicate between the matter particles what they should do. Should I make a bound state? Should I disintegrate or whatever? And the photon is the messenger of the electromagnetic force which is needed to neutralize, for example, the atoms. The gluons are the glue for the strong interaction. They keep the nuclei together, the nucleons and the nuclei together. The Z and W, they are the messengers of the weak force, which is, for example, responsible for the processes in the sun. Without one of these forces, we could just not exist again. That's a fantastic model. It has one problem. We don't know, and Antonio touched this, we do not know how these particles get their mass, these fundamental particles. So this question is unanswered, was unanswered until 2 years ago. How do these elementary particles acquire their mass? Well, I don't know, you might ask why. Why is it important? Well, it is important for you. It's important for you. Because without massive particles, we would just not exist. Because if these particles would all be massless, it would be essentially impossible to form composite matter. It would just essentially be impossible to form us. So that is vital for us to understand how these particles got their mass, because only then we understand why we can exist physically. Okay, so there is one way, and this is the third equation here. What is a possible solution? Well, mass is not only weight, or is not weight really, but mass is also inertia. That means the more massive you are, with the same energy, the slower you move. Yeah? If you are very massive and somebody else is much less massive, you have the same energy, you are moving much less fast than the other person. And that's the equation here, which you see. That's the velocity v normalized to the velocity of light. And you see when your mass is 0, your velocity is the light velocity. No chance to form composite matter. If you have a certain energy and you are massive, you are moving slower and slower the more massive you are. That is. And what do? Well, you introduce a scalar field. Who does not know what a scalar is? I don't believe that. Okay. Don't be too shy. I would not know it either if I would not have done some studies. A scalar is just a number. That means it's something which without any directional preference. A vector, like a river, is a vector because the current goes into one direction. A sea, a lake, if it's a large lake, is a scalar because there's usually no current. So it's always the same. So that's the difference between a scalar and a vector. So you introduce a scalar field, that means it's everywhere the same, and the interaction of a particle with this field gives the particle the mass. And this field is special. It also interacts with itself. So it talks, so to speak, to itself. And that's the Higgs boson. If it would not talk to itself, we would not know that it exists because we would not have the Higgs boson. Sounds abstract, you agree? Okay. Who said that? You. Okay, good, fine. I wanted to be sure that's not one of my colleagues. Okay, so let's assume this is a party of journalists, cocktail party of journalists. They are equally distributed in the room. That's a scalar field. Yeah? There's no preferred direction. Then I open the door on the left-hand side, and I want to go through this field of journalists. They don't know me. Nobody talks to me. My velocity is the light velocity. No interaction with the journalists. I'm through. Then the door opens, somebody else comes in, whom they know. Einstein. I have specifically chosen a neutral person, not to go into any political debate. Now they know him, so they want to interview him. They cluster around him, and he gets more slowly. He gets slow. He acquires mass. The more known the person to the journalists, the heavier its mass, the higher its mass. That's easy. Very easy. So, how to imagine now the self-interaction of the field? Well, I open again the door, and I whisper a rumor into the room. The journalists are curious. What did he say? There's no particle in. It's only journalists. It's a self-interaction of the journalists. That's the Higgs boson. Do you agree that particle physics is easy? Yeah? Okay, the youngsters do. Yes, good. Okay. Well, once you go into mathematics, it becomes a little bit more complicated, of course. Okay, so now, as you all know, the LHC has answered the crucial question in the standard model left open. How do these elementary particles acquire mass? That means we have, most probably, I will come back to that, found the last missing cornerstone of the standard model. However, there's a problem. There are many more questions open in particle physics. Do the forces which we know, which I've had introduced before, do they all unite at the Big Bang, at the high energies? What happened to antimatter? We are in a matter-dominated universe. If there would be no difference in the properties of matter or antimatter, you would not sit here. I would not stand here. We would not exist again. Or is it sure that we are that we are living in 3 space and 1 time dimension? Nobody knows. And the small question, what is dark matter, what is dark energy? Because the standard model is just describing 5% of our universe. 95% are dark, we don't know. 1/4 of it is dark matter. 3/4 is dark energy. Dark matter clumps like normal matter. Dark energy drives the universe apart. We have no idea what dark matter is. We have even less of an idea what dark energy is. Still a lot to do. And I hope that with the Large Hadron Collider, we are now entering the dark universe. Wouldn't that be great? 50 years of research for 5% of the universe? No? A few more years, maybe we go into the 25% of the dark universe, the dark matter. At least director generals are also allowed to have dreams. And this is one of my dreams, to find an indication of dark matter in the laboratory. And that brings me to the Large Hadron Collider. It is the largest, or at least one of the largest scientific instruments ever built, 27 kilometers of circumference. Much more, many more than 10,000 people involved in design, in construction, and now exploitation. It collides the protons, the nuclei of the hydrogen atom, to reproduce the conditions at the early universe. And we do that 40 million times a second with our packets, which we are sending around, 40 million times a second. That gives you the idea. This is one of the magnets of the Large Hadron Collider, which is going down into the underground, where into the tunnel it's transported to its position. At its position, it's connected to its neighboring magnet. And once everything is ready, it looks like this, a boring blue line of cryostats and magnets. But that's how I like it, how the Director General likes it, because once it's looking like this, we can run the machine and run the experiments. It's one of the coldest places in the universe, because we run the magnets at a temperature of 1.9 Kelvin, 1.9 degrees above absolute zero, which is colder than outer space, because outer space has 2.7 Kelvin. So we have the largest refrigerator on Earth. At the same time, it's one of the hottest spots in the galaxy, because when we collide these protons, we produce tremendous energy densities. So if you collide 2 protons at the energy of the LHC, 1 proton and the other proton, it's like a mosquito in full fly on another mosquito. You don't get to the early universe with 2 mosquitoes hitting each other. The key is that this energy is on a very tiny spot. It's on a spot of the size of a proton. That means the energy divided by the size of the proton, the energy density, brings you so close to the early universe. That is the energy density, which is extremely high. So how do we do it? Well, we take 2 beams of protons. So one beam is running clockwise. I have to get it right. Clockwise. And the other beam is running anti-clockwise. So one is running in the blue tube and the other one in the red tube. And we have altogether 2,800 packets in one tube and 2,800 packets in the other tube as of next year. Until 2 years ago, we were only running 1,400 packets. But okay, that's a small thing. Each packet contains roughly 100 billion protons. So 100 billion protons in each packet running like this, and 100 billion protons in each packet running the other way. And then at the positions where we want to measure the collisions, we bring together, we collide these packets. And when we do that correctly, 10 to 40 of the protons are colliding, are interacting. And of course, the protons consist out of the quarks and the force particles. They break into these quarks and force particles, and these constituents then interact at this very high energy density, and out of this interaction of these quarks and gluons, new particles come out, and we interpret the image which we take of these collisions and of the products out of the collisions. We interpret the physics which happened at the beginning of the universe. So in order to illustrate that, that gives you an idea. These are the blue magnets. The protons are running inside, and I have collected, they cross the border, it's in Schengen, that's okay. This is a proton with its quarks inside, which are bubbling around. And then from either side of the huge detectors, the protons are coming. And then, if you do it correctly, they collide. Zack. And out of these collisions, other particles are coming out, according to Einstein. E equals mc squared, you make a lot of particles. And then you have to register these images and to interpret these images. And there are many, many particles coming out, and then you have to be able to select the right particles in order to find the new physics. And if you look at this image, please keep in mind the white traces are not important. What is important to remember are the blue ones. And you see 2 blue ones go to the top left and 2 blue ones go to the bottom right. So altogether 4 blue tracks. Remember these, I come back to these later. 2010, we started the Large Hadron Collider at an energy never obtained by mankind before, at the energy of 7 TeV, 2 years later, 8 TeV. We have 4 collision points, and at each point, we have huge digital cameras, huge detectors which register what is happening. Now, it is very difficult for you to see if you put the, yes, here, if you look on the bottom right, do you see the human person there? You need good eyes to see the person, but there is one on, but it shows you that these detectors are huge. So the bottom right one, called Atlas, is 25 meters wide, 25 meters high, and 45 meters in length. It's all equipped with instrumentation now, and with around 150 million sensors. CMS, the other on the top left, is smaller, 15 times 15 times 25 cubic meters. And you need at least 2 experiments to cross-check each other in order to be sure that you found something new. And these detectors, they take the signals of the collisions and interpret these signals and then look into the physics. Now, why does it take so long to find physics? First of all, this gives you a better impression of the detector. Here you see CMS, the smaller detector, and you see the 2 people on the bridge between the detector pieces which are being mounted at the moment. And each of these experiments have around 3,000 members for more than 40 countries. 3,000 members means at least 200, 300 professors. 300 egos. Yeah? You have to get these 300 egos together. Of course, they have some excursions, we have to get them back again. I can tell you, it works. Once you have a common goal, it works. You can get this. You can get more than 300 egos together, but it's fantastic. I mean, because everybody knows I cannot do it alone. I need the other, and the other one knows I need him or her. So there's competition, but also cooperation. That's important. And these are some of the questions which we can address. What was matter like in this hidden universe before it was 380,000 years old? So what was matter like? That's one thing we want to find out. Have we found this Higgs particle? Will we find the reason why antimatter and matter have not completely destroyed each other? That's important to understand. And the small question, will we find these particles of mysterious dark matter and what is dark energy? So will we get some access to the 95% of our universe? Aren't these interesting questions? I think they are. Okay, now why does it take so long? Well, if you look onto this diagram, on the top you have a horizontal black line. This indicates the sum of all processes which happen when protons are colliding. And then you have around 10 orders of magnitude below, you have the red curve, which is, for example, new physics. So there is a difference of more than 10 orders of magnitude between the total rate of events which can happen and the interesting new physics. That means you have to select one out of more than 10 billion events until you have an interesting one. Okay, the other stuff is also interesting, but not earth-shaking. The new one is really earth-shaking. So what does it mean? You need high statistics. You need tremendous amount of collisions. You need many years of data collection. And you need, of course, sophisticated programs in order to evaluate and to check your images. So now I concentrate on that one, on Higgs, because time is running out, I guess. I'm not sure, but okay. That again shows you the production rate of Higgs bosons, for example, again compared to the total production rate possible at the LHC. You see again the 10 or more than 10 orders of magnitude difference. That's one thing. But now comes the other complication. Now this Higgs boson has to give mass to other particles. That means it has to talk to each particle. If it does not talk to you, you are massless. If it talks to him, and he's a tiny guy, it doesn't talk very often to him. But if it talks to something which is very massive, it talks very long. It has a high intensity. That means it talks to each particle. That means each image can be different depending on the particle to which the Higgs particle talks. So this is why the images in the detector can be completely different. So you have a huge variety of different images. Now you need many collisions in order to produce it, but you need even more because it can appear in different images. And I showed you one of the image. You remember the two blue tracks going to the left top and the two blue tracks going to the right bottom. These were muons, particles of the cosmic ray. And two muons on the one side and two muons on the other side could be the indication of a Higgs boson. And that is this decay mode, which is indicated now in the blue rectangle. This would be one indication of a Higgs boson. But it could also be a background. So you need a lot of statistics to identify it. But you have another very clean channel, and that's the one with two photons inside the red circle. Again, you can have many processes where two photons could appear in your image. But if you have these processes, if you plot then your result, it would be a curve, a constant line. But if you have on your constant line a small mountain or small hill or whatever, then you found it. If you have a deviation from the line, you have it. First of all, it looks like this. We can drop that. That's it. Yeah? This was on the 4th of July 2012, the finding of the Higgs boson. The continuous line is what you expect without the Higgs boson. And then you have around 125, you have this, in German it's a pickle, I don't know what is in, something which sticks out. You have a small mountain on it, a resonance. That's the Higgs boson. That was the plot for the discovery of the Higgs boson. Now it becomes complicated. I want to guide you through 1 year of huge excitement at CERN and in the world, at least in the world of physics. This looks complicated, is by no means complicated. Well, okay. What this displays on the horizontal axis, you have the mass of a possible Higgs boson, here in the range of 110 GeV to 150 GeV. The vertical scale gives you the probability that when you see some deviation, that it is not No, that it is a fluctuation. I always get it wrong. It's the probability that it is a fluctuation. July 2011, we had fluctuations everywhere, okay? But there was already something around 125, very small fluctuation. But if you have nothing else, you get already excited. So one has to dampen a little bit the excitement. Then in December 2011, you see everything is flat. No fluctuation, nothing. And then at 125, you suddenly have something which has a probability of roughly 0.5 per mil or so of that it would be a fluctuation. So it's already a very good indication around 125. So then people got really excited. Then the analysis continued and it went back a little bit from 0.5 per mil to 1 per mil. But that's a lesson again to the young people. If everything in science always goes in the same direction, something is wrong. There has to be a fluctuation. Okay, so that was nothing which was problematic for us. And then came July 2012, and you see again everywhere flat, no problem, no signal indication. But at 125, we have now a probability of less than 3 million that we have a fluctuation. This is called 5 sigma, and this is for us the time or the moment when we can call discovery. 5 sigma is our limit. And then the analysis went on, a bit more data, and you see it got even stronger. So probability of a fluctuation 10 to the minus 9. So this is a textbook plot how within 1 year things are evolving and pointing towards a discovery. And it also shows that it takes time. And actually, I must say, it was much faster than I personally would have expected. So it took only a bit more than 1 year. But I can tell you, it was an exciting year. And there are times which are much worse to be for a director general to be director general, I can tell you. That was a great moment. Okay, so it made, of course, a publication in our scientific journals, but also, for example, in The Economist. Now, why have I chosen The Economist? Because I like very much that The Economist talks about science. It doesn't talk about particle physics or physics, it talks about science. And we should always keep in mind, whatever discovery we make in our field, it's for science in general. That's very important to transport the excitement of science into not only into the scientific, but also in the general public. Okay, but is this new particle really a Higgs boson? Does it do its job? Once it does its job, it needs to talk to the low mass particles much less than to the high mass particles. And this plot shows you on the horizontal axis the mass of the fundamental particle, and on the vertical axis the speaking frequency, so to speak. And you see, for the low mass particles, it doesn't speak very often. For the high mass particles, it talks very often. So it does its job within the error bars which we have. Still a lot of work to be done. But the question is it a scalar field or not? So they have measured its property on the spin, and the conclusion is it has spin 0. It is a scalar field. Conclusion? Yes, it is a Higgs boson. It completes the standard model. Now, after 50 years of research, we can describe around 5% of the universe. It's a big success. No, it is a big success. And I see my colleague laughing. Miguel, it is a big success. Okay, you agree?
Yes.
Okay. Yeah. Nobody contradicts the Director General in the open. Privately, yes, it's okay. Okay. Of course, the Nobel Prize Committee has realized this and recognized this, and this gave the Nobel Prize in Physics 2013 to François Englert on the left and Peter Higgs on the right. The particle is named after Peter Higgs. However, you can read the green text that their theory was confirmed through the discovery of the predicted fundamental particle by Atlas and CMS at CERN's Large Hadron Collider. We did not get the Nobel Prize. Tant pis. We are inside. That's the main thing. Can you imagine these two guys? They wrote independently their publications 1964. So 48 years before the discovery. The first time they met ever personally was on the 4th of July, 2012 at CERN. It's amazing. But it's fantastic for these people. 48 years ago, they wrote it, and then they are still alive when we find the particle. It was an emotional moment, I can tell you. Okay, but now I have to tell you one more thing before you are relieved. The Higgs particle is something very, very special. Because all matter particles, all the quarks, electrons, etc., they are fermions. That means they have a property which is called spin. It's difficult to imagine a pint-like particle spinning, but okay. We call it spin. And they have a spin which is it's quantized, but they have a spin. All the force particles are bosons which also have a spin. So all known particles until 2012, all fundamental particles have spin. Matter particles have spin, force particles have spin. The Higgs particles are spin zero. They are scalars. They are neither matter nor force. So they are different. The Higgs is different. The Higgs particle is the first and up to now only fundamental scalar in our hands. Well, it decays very quickly, but we have it. Yeah? We can investigate it. So it is the first fundamental scalar ever discovered. Now, dark energy drives the universe apart in all directions in the same way. So it's a scalar. So why should investigation of the Higgs boson not reveal maybe some hints on dark energy, on the behavior of dark energy? I'm not saying it's the same. That's definitely not. However, there is a connection because both are scalars. And why should the Higgs boson be the only one of its kind? Why should there not more scalars? So the door is open to discover more scalars and to investigate them. But the big difference is that now for the first time we have a scalar which we can investigate. And this is very important. So what's next? Well, we know it is a Higgs boson. We don't know if it is the only Higgs boson or if it is part of a family. As soon as we would find out that it's part of a family, it would open a door in the dark universe. Because the properties of the Higgs boson could give information on dark matter, but it could also give maybe first hints on dark energy. Imagine, after 50 years, we could maybe open the first window into the dark universe. So I must say, at least my understanding of the universe is about to change with all this new stuff. And this is why we have set up now a program in order to study all of this at the Large Hadron Collider until roughly 2035. So for the next 20 years. This is our short-term plan. The long-term plan goes beyond 2050 with maybe a new collider, but that's a different story. So, the past decades, the past 50 years, saw precision studies of just 5% of our universe. And I call it the discovery of the Standard Model. It's really a discovery. The LHC delivers data, and after 3 years running, we have already a fundamental discovery, a fantastic discovery. To my mind, we are just now at the beginning of exploring 95% of our universe. And I can only say the future is bright in the dark universe. Thank you.